I don't have a page number up here, but you guys are all intelligent enough. You can find the page. I guess it's 28? 28. What we're doing is solving trigonometric equations today. And I know there are a couple of you that you've come to me and you've said, I need some extra help or some extra practice or extra examples, and I've directed you to the textbook. Even though you were not assigned a physical textbook this semester, you have access to the chapters. So I want to just take a minute and explain why this is 4.3 Part 2 and 4.4 Part 1. In 4.3, you learn about all those things we did yesterday, but you also learn about how to find an angle. That's how it's approached in the previous section. How do you find an angle? And then in 4.4, among other things, we solve trig equations. But when you solve a trig equation, you're finding an angle. So there's no difference between what's being taught at the end of section 4.3 and what's being taught at the beginning of section 4.4. We're solving trig equations today. And sometimes you're asked to solve trig equations over a specific domain. And sometimes you're asked to solve them over the domain of all real numbers. We will learn very quickly that every trigonometric equation, if it has a solution, it actually has an infinite number of solutions. And the basic reason is if theta equals 30 degrees is a rotation angle that's a solution, you can add 360 to that and be in the same place and get the same solution. Or take away 12 times 360 and you're still going to get the solution. So to begin with, consider this equation. It's a very basic equation. Sine of theta is equal to 1 over 2. It's an equation. It has an equal sign and it has an unknown variable theta. We could go to the unit circle. Okay, we could go to the unit circle and I will just mime it up here. And when you go to 30 degrees, it's this point right here that's at the tip of my finger. The y coordinate is the value of the sine of the rotation angle, and the y coordinate there is 1/2, isn't it? And when you go to 150 degrees, you're 30 degrees away from 180. You're in quadrant 2. It still has a reference angle of 30 degrees, which is why these are both solutions. That's part of it. But the y coordinate here, which is the sine of theta, is 1/2. So you could, draw all that. Or you could just put your calculator in degree mode and go sine of 30 equals 0.5, sine of 150 equals 0.5. You don't have to do that. I'm just telling you it's a trivial thing. Okay? Done. I don't know. We don't need to write anything here. Do all rotation angles coterminal with 30 make it true? Well, ultimately, the reason why sine of 30 degrees is equal to 1/2, ultimately it's because on the unit circle at 30 degrees, the y coordinate is 1/2, right? So what will the y coordinate of the point on the unit circle be for any coterminal angle with 30? Well, coterminal means you still end up in the same place. Whether I say this is 30 degrees, or whether I say it's 390 degrees, which would be 360 plus another 30, or whether I say it's negative 330, I end up in the same place. The angle is different. The destination is the same. The location is the same. So we're going to have to distinguish here in this lesson between a rotation angle and a location. They're not the same thing, necessarily. And the same with 150. I'm not going to draw it, but if you draw a rotation angle of 150, the reason why sine of 150 is equal to 1/2 is because at 150 degrees, the y coordinate there is 1/2. So if you rotate around an additional revolution, you're still going to be at the same point. You'll still have the same y coordinate. So, I don't know what we want to write there. But yes. And I'm just trying to illustrate to you that an equation, even an equation so basic as the one at the top of the screen here, even an equation that's that basic and that's trigonometric has an infinite number of solutions. It has 2 solutions between 0 and 360. But over the domain of all real numbers for theta, it has an infinite number of solutions. Write the general solution to this equation then. Well, first of all, I want to write this. I just want to make sure that you understand something here. If this were the case, the solution would be that. That is not what question D asks. Okay? But if it just said solve the equation for angles greater than 0 but less than or equal to 360, you'd say 30 degrees and 150 degrees, right? So what would the general solution be? The general solution is 30 degrees, theta equals 30 degrees plus 360 degrees n, where n is an integer. Will that statement produce 30 degrees as one of the answers? Yes. Because the integer condition tells you that 0 can be a value of n, so 30 degrees plus nothing is 30 degrees. That is one of the solutions. And theta is also equal to 150 degrees plus 360 degrees n, where n is an element of the integer number set. So this is what we're going to spend the bulk of the lesson on, is solving over a specific domain, and then we'll talk about general solutions. So let's take a look at example number 1a. And I moved things around in this unit, so please just double check for me that this matches your 1a. Okay. I want to point out to you that this is a Math 20 question. There's nothing new about this. In Math 20, you were taught that to solve a trigonometric equation, you have two things to find. The reference angle, you need to know the reference angle, and you need to know the quadrants that the terminal arm might lie in. Does that vaguely ring a bell? Slow nods of the head for some of you, and that's okay. The fact that cosine of theta is a positive number tells us that the two quadrants will be quadrant 1 and quadrant 4. Because cosine, this is all, we're not learning things that are disconnected from each other. This is all connected. Cosine is x over r. Whether we're talking unit circle or not, cosine is directly associated with x. And if cosine is positive, you say, well, where is x positive? It's positive over here in these two quadrants. If the center of my chest is the origin, I'm talking about these two quadrants, which is quadrant 1 and 4. So we can figure this out. This is easy. 1 and 4. How do we find the reference angle? Well, who remembers how to find a reference angle? Inverse cosine. We just take the inverse cosine. Although, and if I had to change my notes, I would have changed this. Even if this were negative, which would change the quadrants, the reference angle is found by ignoring the negative. Okay, and we'll get to definitely one example of that later. But basically, the reference angle will be equal to the inverse cosine of 0.5240. And we want answers in degrees, so this is what's different here. Well, it's not really. In Math 20, I would have just said, put your calculator in degree mode because that's what we always want. In Math 30, I'm saying to you, put it in degree mode because that's what we want in this question. If we wanted it in radians, then we'd be in radian mode. So I take the inverse cosine of point, what are we doing, 524, and you get 58.4 degrees. So the reference angle is 58.4 degrees. Are you with me on that? Is it coming back to you now? Okay, and then what your Math 20 teacher would have instructed you to do is put these two ideas together, these two things that we found, this and this to find rotation angles. Don't forget a reference angle. We haven't really reviewed this, but a reference angle is simply the angle between the terminal arm and the x-axis. It's the smallest angle. So when I draw this in quadrant 1, and I would recommend until you get really proficient at this to draw 2 of these. Can you answer the question by putting these both on the same grid? Yes, but it's confusing. Okay? So in quadrant 1, we're going to sketch a rotation angle that would give us a reference angle of 58.4 degrees. And that's the reference angle. That green arc is the reference angle. It has no direction. It has no direction. It's just an amount of an angle. The rotation angle is going to be that. And whenever you see theta, just theta with no subscript, that means rotation angle, not reference. In quadrant 4, we're going to draw a terminal arm so that we have a reference angle. And again, there's no direction to the reference angle. A reference angle of 58.4. It's always from the terminal arm directly to the x-axis in that quadrant, not swinging around the other way. And that means that theta is that. And then you just use your knowledge of angles to find out what theta is. In this particular case, theta will simply be 58.4 degrees. So that is one of our 2 solutions. In this situation, we have to take 360 degrees and subtract that reference angle to get 301.6 degrees, I think. So you can check that for me. Is it 301.6? Was my calculation correct? Okay. And we're done. What is in red are the answers to this question. The solution to cos of theta equals 0.5240 in the domain from 0 to 360 are these 2 numbers. We're good? Okay. So there's a number of things that are different here now. In this example, and does it match yours? In this example, we're dealing with radians. The domain is from 0 to 2 pi. It's also not math 20 because there's a reciprocal trig ratio there, and there's a negative as well. So the first thing to note is that if you're going to find a reference angle on your calculator, you can always go inverse sine or inverse cos or inverse tan, but you do not have a cotangent key, so you could never go inverse cotangent. You do not have a secant. You can't go inverse secant. And you can't go inverse cosecant. So we have to use our knowledge of trigonometric reciprocal ratios to write this as a primary trigonometric ratio. And it is so easy to overthink what's going on here. Sine is the reciprocal of cosecant. So if cosecant is this number, sine is the reciprocal of that number. That's it. Sine will be equal to 1 over negative 1.6588. We don't need to calculate that. If you calculate it, you're going to introduce a bunch of decimals that you have to keep track of. That's what sine of theta is equal to. So we need to find the 2 quadrants. Sine is negative. If you take a look at what I've just written, sine is a negative number. Sine is directly connected to the y coordinate of a rotation, of a point on the terminal arm of a rotation angle. Directly related to y. Y is negative down here. So sine is negative down here. Does anybody remember from last year being taught like the cast rule or things like that? I think at this point you just have to reason it out every time. You should know that sine is negative in quadrant 3 and 4. What that means, everybody, is in a minute, once we know the reference angle, we're going to be drawing a terminal arm in quadrant 3 with that reference angle that we don't know yet, and a terminal arm in quadrant 4 with that reference angle that we don't know yet. But we want answers in radians. And this becomes a little problematic, but let's begin by putting our calculator into radian mode. And the reference angle, theta reference, will be equal to the inverse sine of whatever 1 over 1.658 is. You do not, 6588, you do not include a negative with your reference angle calculation. Very briefly, you can do it if you do include it, but then I would have to teach you that there's a different set of rules for what to do if it's sine, then if it's cosine, then if it's tangent. There would be 3 different sets of rules if you included the negative. So the reference angle is never found using the negative. So what do we get for a reference angle? I guess I've got this laid out from last semester. I go inverse sine of 1 divided by 1.6588. Make sure that's right. And I get this. And here's where things get peculiar in your brain. If you got, I don't know, if you got 70 degrees, you know what that looks like, right? You don't necessarily know what 0.65 radians looks like, but don't convert it to degrees. It's not going to be 70 degrees, by the way. You should know that 1 radian is pretty close to 60 degrees. You should know that this, which is 90 degrees, is pi over 2, which is about 1.57 rads. So it doesn't, and it turns out it doesn't really matter. You know this angle that you found is less than pi over 2 because it's a reference angle. So you sketch it here. You sketch it here. Do that again. And you sketch it here. And what did we get? 0.647? So theta reference equals 0.647 rads approximately. This is 0.65. This is 0.65. Don't forget, these are just reference angles. How do we find the rotation angle, which will be this in quadrant 3 and this in quadrant 4? Well, if we were working in degrees for the quadrant 3, we would take 180 plus the reference angle in degrees. But we're working in radians, so it's going to be pi plus the reference angle. So your theta here is pi plus 0.65, and here it's going to be 2 pi minus 0.65. I think we were asked to the nearest decimal, right? So we have to take pi plus go with 0.647. And what do we get? Let's just add pi. You get about 3.8. And if we take 2 pi, and subtract that reference angle, we get 5.6. So 3.8 and 5.6. 3.8 rads, 5.6 rads. Are we okay with that? Okay. Okay, tan of theta equals root 3. And we want it in radians. Well, the only thing we have to do to begin with is first of all get this primed for a reference angle. We want to know what the reference angle is. I guess we can also say that we know the quadrants. This requires a little bit more thought than A or B. The quadrants are going to be quadrant 2 and 4 because tangent is y over x, and it happens to be a negative thing in this question. And the only way y over x can be negative is if either y is positive and x is negative, or the other way around, whatever the opposite of what I just said is, because I forgot which one I chose. And in this quadrant here, in quadrant 2, you're dealing with a negative x and a positive y, and in quadrant 4, you're dealing with a negative y and a positive x. Now, this requires practice and skill like anything else in this course. You'll notice that root 3 or negative root 3 is a very precise number. It's not a decimal. It's not some kind of weird decimal. And for these reference angles, we got like we got, to be honest, irrational numbers for the angles. But you should know that on your unit circle, those special points have exact, precise values for x and y. So even though this is in radians, I think it's smart to put your calculator in degrees and see if the reference angle is something you recognize, because you might be asked to do this as exact values. Okay? So if I do, and by the way, I better write this down. The reference angle will be the inverse tan of root 3, right? Not negative root 3, of just root 3. So what do we get? And again, I'm telling us, even though it's in radians, we want an answer in the end in radians, our spidey senses are telling us, I think this might be one of those special angles because it's root 3. It's not 1.6. It's actually an exact value for an irrational number. So I put my calculator into degrees, and I go inverse tan of the square root of 3, and I believe we're going to get 60 degrees. So what we've done is we've kind of cheated the system behind the scenes, and if this were a exam written response, we could say that pi over 3 is the reference angle. Right? If you put your calculator in radians and went inverse tan, you would get whatever pi divided by 3 is. It's going to be 1 point some weird number. And now we can draw that reference angle in quadrant 2 and in quadrant 3. This is pi, or 4 rather. This is pi over 3 as a reference angle. This is pi over 3 as a reference angle. I'm drawing them maybe bigger than they need to be. I don't know. I have a hard time judging angles. So what is the rotation angle? What is theta? What is theta? Well, do not, to find theta here, do not say that theta in quadrant 2 is 2 pi minus, or is pi minus pi over 3. I mean, you can do that, but just count it off. It's 2 pi over 3 to get to that point, right? 1 pi over 3, 2 pi over 3. I'm just checking here. Is there a question at the back of the room? You're good? Okay, I just wanted to make sure. And over here in quadrant 4, it would be 1, 2, 3, 4, 5 pi over 3. So we're back to that thing that I had mentioned when we first learned about radians. Sometimes it's easier to find angles when you're thinking in terms of radians than degrees. It's a counting game. We're okay with that one? Is this the same as your handout? Okay. Well, if we start to rearrange this for sine of theta, we can add root 3 to both sides and get this. And here's where we take an enormous leap in the procedure. Can you find a reference angle here and do all of that stuff? Yes. But you should know, everybody, that the two locations where sine of theta is root 3 over 2 are pi over 3 and 2 pi over 3. Your brain should say, wait a minute, root 3 over 2 is one of those numbers that we've become familiar with. So you would say to yourself that sine is y. This is y equals 1. Oh, right. These are the two places where the y coordinate on the unit circle is root 3 over 2. I mean, I can put in the coordinates if you like. This would be 1/2 root 3 over 2. This would be negative 1/2 root 3 over 2. But those are the two places. So then what is the rotation angle that takes us to here? And here, I don't have a problem with you putting them both on the same grid because you're not really working with reference angles. It's not going to be cluttered. This is one of our solutions. This is another of our solutions. It's pi over 3 and 2 pi over 3. And that's why I said when we learned the unit circle, there's a part of knowing the unit circle that just makes your job so much easier. You don't even have to be careful here. If it's a written response, you better explain that by maybe drawing what I drew, saying that on the unit circle, those are the coordinates, and sine of theta is the y coordinate. So it's pi over 3 and 2 pi over 3. I guess I never really wrote it down, did I? And by the way, we want it in degrees, so it's 60 degrees and 120 degrees. Now, there are going to be, in any Math 30 class, there are bound to be a student or two or three or however many who are not successful with the unit circle. Then find the reference angle in degree mode, see it's 60 degrees, draw it in the two appropriate quadrants. E, cotangent minus 1 is equal to 0, and we have what I call an oddball domain. We want from negative 3 pi over 2 to 2 pi. So the first thing to do is get this as a single trig ratio equals a number. Then, since it's cotangent, we can say tangent is the reciprocal of cotangent. If this is cotangent, tangent is the reciprocal of that, which is still going to be 1. Okay? So we have tan of theta equals 1. Okay. 1 is a very precise number, so we suspect that the reference angle, if you're going to go that route, we suspect it's a nice angle, which would mean, and I don't want you to do it just yet, if you did go inverse tan of 1 on your calculator, it would be a smart move to be in degree mode. I don't want you to do that. I want you to think about the fact that tangent is y over x. So what does it mean to say tangent of theta is going to be 1? It means that y and x are the same number. And right away, what we have determined by saying that is that we know the two locations where this happens. Not the angles, the locations. We know that up in quadrant 1 at the pi over 4 reference position, at the 45 degree reference position, x and y are both root 2 over 2. And in quadrant 3, 180 degrees or pi radians further than the one in quadrant 1, we know the x and y coordinates are negative root 2 over 2, comma, negative root 2 over 2. They're the same. So these are the two locations. When you have a strange domain, here's my best advice I can give you. Solve for this first. Or in this case, solve for this first. Don't worry about the weird domain. Just find those regular run-of-the-mill angles. So those angles, which are actually rotation angles, they are solutions, maybe, we'll get to that in a second, will be pi over 4 will be pi over 4 and 5 pi over 4. 1 pi over 4. 2, 3, 4, 5 pi over 4. Right? Those definitely have tangents equal to 1. Now what you do is the following. You can do it in a number of different ways. Okay? But I think the most students will have the most success if they follow this procedure. Draw a number line. And on the left side of the number line and on the right side of the number line, put your maximum and minimum values that you're allowed to have for theta. It says from negative 3 pi over 2 to 2 pi. So 0 is someplace in here, right? 0 is probably about here. And we start off with the pi over 4. Is pi over 4 in this domain? Definitely. So we can write theta equals pi over 4. But if you add 2 pi to pi over 4, you get the same location. Which means whatever pi over 4 plus 2 pi is, that's a solution to tan theta equals 1. So what you do is this. You say, well, I'm going to take pi over 4. This is kind of just off on the side. You're thinking about this or you're writing it down. And I'm going to add a full revolution. And a full revolution is 8 pi over 4. You can either convert 2 pi to a denominator of 4, or you can go 1, 2, 3, 4, 5, 6, 7, 8. You can count them off. This will give us 11 pi over 4. Is 11 pi over 4 in this domain? Well, it only goes up to 2 pi. And we've taken pi over 4 and we've added 2 pi to it. This, by the way, is 8 pi over 4. 11 pi over 4 is past the barrier on the right. So this is not a waste of time. We've done this so we know it's not a correct answer. However, I can also take pi over 4 and subtract 8 pi over 4. That would also give me an angle that would land in the same place where tangent is 1. Well, that's negative 7 pi over 4. Well, is that in this domain? I can't answer that without doing a little bit of math. One of the things that I would probably do is I would say that this is negative 6 pi over 4. I want to compare pi over 4s to pi over 4. So negative 3 over 2 is negative 6 over 4. So is negative 7 pi over 4 in this domain that's indicated by the number line? No, it's outside of the left-hand barrier. So this particular location right here has, in fact, in this question, only one solution, pi over 4. We've exhausted all of the possibilities for that. So now what we do is we go to 5 pi over 4. Is 5 pi over 4 in here? Sure. You know, if this is 8 pi over 4 and this is 0, 5 pi over 4 is in here. How many of you see that if I add a full revolution, which is 2 pi, to 5 pi over 4, I will bust past this fence? Right? I'm going to get 13 pi over 4. So I've exhausted the possibilities for going forward. But what if I take 5 pi over 4 and subtract a full revolution? Well, what do I get? I get negative 3 pi over 4. Negative 3 pi over 4. And by the way, some of you will recognize that that's the case because that's negative 1, negative 2, negative 3 pi over 4, right? And I can tell that I think some of you were just doing that in your head anyway. Is that in this domain? Well, this goes back to negative 6 pi over 4. This is not quite at negative 6 pi over 4, so it's in the solution. So these are the three solutions. And just to finish this off, I hope you see that if you take negative 3 pi over 4, which will be here, and subtract 2 pi again, you're outside of the domain. Okay? All right, one more, and then we'll finish this off with the final example, which will take just a couple of minutes. What do we get here? We get secant of theta equals negative 9 over 5. You're okay with that rearrangement? That means that cosine of theta equals negative 5/9. Is it obvious to many of you that that's not one of those special points? I mean, is there a point on the unit circle that has an x-coordinate equal to this? Yes, but we don't know what it is. So we're just going to go to the calculator. We're going to find a reference angle. And seeing as how we're winding down this lesson, I don't think we need to write anything here. You're simply going to put your calculator in degrees. Take the inverse cos of 5 over 9, no negative, and get a reference angle of 56 degrees. Well, 56.3 degrees. You're going to say, and I really think diagrams are helpful here, that we are going to be looking in these two quadrants because cosine is negative, and that means x is negative. So the positions will be indicated by these two terminal arms. These are just positions with reference angles to tell us where they are. What does that mean? Pretty easy calculation. 180 minus 56.3. How is my subtraction there? Yeah. And then here, theta will be 180 plus 56.3. How's my addition? Okay. So now, we don't need a number line for this because this is in degrees. Are these two numbers both in this domain? Let's start with the 123.7. Is 123.7 between negative 180 and 180? Okay, so 123.7 is a solution. I really don't believe I should have to do this. But if I take 123.7 and add 360, am I going to get a number that's in that domain? I mean, how many of you see that adding or subtracting 360 from that is going to bust you outside of the borders? I mean, it only goes from negative 180 to 180. So, you know, we can do this and go, oh, surprise, it's more than 180. Or you could go 123.7 and subtract 360. Well, that one might require a little more thought, but that's outside of the domain as well. So this particular quadrant has one solution. Is it 237.3 or 236.3? Okay.
It's 36. You just added 361.
Right, but this number is correct. Okay, I thought maybe there should be some symmetry between these numbers, but there isn't. Is this number for the rotation angle that terminates in quadrant 3 in that domain at the top of the screen? No. I hope you're not going to waste your time by adding 360 to see if you get something that is in there. But what if you take away 360? What do you get? So 236.3 subtract 360, oh, negative 123. So here are our two solutions. They both, by the way, correspond to this position. No, they don't. This is that one, this is the other one. Good? Okay, I just want to run through the final example very quickly. I already spent some time at the beginning of the lesson explaining this, so I hope it makes sense. If you were to go back and look at example 1a, we solved this equation. Do you remember it? Is it vaguely familiar? If you were to go back and look at the solutions, we got 58.4 and 301.6, correct? Can somebody flip back and confirm that? That was the solution for 0 to 360. If I said what is the general solution, which is what this is asking, I would say theta equals 58.4 plus 360 degrees n and 301.6 plus 360 degrees n, where n is an element of the integers. That's all we have to do for this. If any of those questions didn't say 0 to 360 or 0 to 2 pi, we would write out the general solution. So for example, in B, I believe we got 3.8 and 5.6 radians when we solved this. So what's the general solution? Theta would be 3.8 plus 2 pi n, 5.6 plus 2 pi n, where n is an integer. They're in radians, so we have to add multiples of 2 pi because 2 pi is a full revolution. So, what would the solutions in C be? The general solutions? 2 pi over 3 plus 2 pi n, 5 pi over 3 plus 2 pi n. N is an integer. I feel as though you should be able to figure that out almost on your own. And over here, I think for D, we got 60 and 120, didn't we? So that would be, as a general solution, 60 degrees plus 360 degrees n, and 120 degrees plus 360 degrees n. Again, you have to put that description of what n is there, and n is an element of the integer number set.